Hello everyone. Today we will be starting with the last session of the chapter hydrogen and its compound. So this is the session 5. Today we will discuss about peroxide, that is H2O2. Some things about hydrogen economy. We will just have an idea of it. Right. So these two topics we will be covering in today's session. Students are requested to drop down their names for attendance purpose so that we can start in a while. Students are requested to drop down their names for attendance purpose so that we can start in a while. Okay, so we'll start with the session. See, today the compound that we have to study for hydrogen is hydrogen peroxide, right? Previously we have covered water and heavy water, that is D2O. Today we will study about H2O2, that is known as what? Hydrogen peroxide, right? So what are the basic properties of hydrogen peroxide? It is basically colorless and syrupy liquid, right? And it has the odor like that of a nitric acid. However, it is soluble in water, alcohol and ether in all proportions. And with water, it forms a hydrated compound as H2O2.H2O. Right? So in water, it forms a hydrated compound. Coming on to the melting point, it is 272.4, whereas the melting point of ice, if you take, or water if you take particularly, it is 273. Right, so melting point of peroxide, if you will compare with that of the water, it is somewhat approximately equal or lower than that of water. Then boiling point is 423 Kelvin, and the boiling point of water was what? 373 Kelvin, right? So boiling point of peroxide is higher than that of water. Next, you come on to density. In solid form it is 1.64, in liquid form it is 1.44. Viscosity, you give it in centipoise, that is Cp, abbreviated as Cp. It is 1.25. Viscosity, you denote it by eta, and its unit is centipoise. Then you come on to dielectric constant, same as that of what we compared for water and D2O. Here you will see the dielectric constant of peroxide is 70.7, and electrical conductivity in ohm inverse, centimeter inverse or Simon centimeter inverse is 5.1 into 10 raised to the power minus 8, right? Amongst these properties, you can only learn the melting point and the boiling point. That is sufficient from the examination point of view. You should just know the approx values. Melting point is somewhat same as that of water, however lower than that of water rather. So 272.4, and boiling point is 423 Kelvin. Now next you come on to the structure. So structure is the area from which the questions are asked, particularly for hydrogen peroxide. So here you will see it has a open book type structure. Its structure is known as open book like structures, right? So it is somewhat like this. Can you see here? Here, right? So this angle is known as what? The dihedral angle. So in gas phase, the dihedral angle comes out to be 111.5 degree, while in solid phase this angle reduces to 90.2 degree, right? Remember the structure of peroxide, that it has a open book like structure. You can see the structure is like that of open book like structure. Okay, and this particular thing you should remember, that in gas phase the dihedral angle is more, while in solid phase the dihedral angle is approximately equal to 90 degree. Now methods of preparation are important. So what are the methods of preparation? So treating barium peroxide with H2SO4. Remember, it is not oxide, it is peroxide, because if it is barium oxide, what is the formula of barium oxide? Barium is having +2, this is having -2. So this will be crisscross method, barium oxide will be this. And BaO2 is what? Barium peroxide. Okay. So barium peroxide, when you treat it with H2SO4, it gives you what? Barium sulfate as PPT and H2O2 in aqueous form. This is important, right? So this is the first method of preparation of peroxide. Next is that particularly electrolysis of HSO4 negative will give you peroxo disulfate. This is what? Peroxo disulfate. Actually, this linkage is known as what? Peroxy linkage. This particular linkage is known as what? Peroxy linkage. So peroxo and then disulfate, SO3H and SO3H. So this is known as what? Peroxo disulfate. So on electrolysis we obtain this, and hydrolysis of peroxo disulfate will give you what? H2O2. This will give you peroxide in aqueous form. Okay, now this particular method is also used for the preparation of D2O2, means when you replace hydrogen with one of its isotope, so deuterium that is, so it will become D2O2. So for preparation of D2O2 we use the same method. We treat K2S2O8 with D2O, which will give you D2O2 in liquid form and KdSO4 in aqueous form. Okay. So these are the methods of preparation. Now industrially, particularly in large amount, how will you prepare H2O2, right? Because for the industrial use we prepare it in a large amount. So 2-ethyl anthraquinol, right? This is known as anthracene. This particular 3 benzene rings attached to each other is known as anthracene, and then 2 OH groups make it what? Anthraquinol, and second position will have what? Ethyl group, right? So 2-ethyl anthraquinol on reaction with oxygen, that means in the presence of air and in the presence of hydrogen and palladium, right? So it gives the H2O2 plus the oxidized product. So when you particularly oxidize alcohol, you will get secondary alcohol. When you oxidize, it gives you ketone. This all you will learn in organic chemistry in detail, right? So here what happens, that the alcohol group oxidizes to ketone and the product that is yielded is peroxide. So in this you just have to remember that industrially how peroxide is prepared, that 2-ethyl anthraquinol on reaction with air in the presence of hydrogen and palladium will give you H2O2 plus 2-ethyl anthraquinone. Okay, so alcohol has been changed to ketone. The one which is having OH group is known as alcohol. The one which is having C double bond O group is known as ketone. So this is a ketone and this is an alcohol. Now from sodium peroxide, how it can be prepared? This is known as Merck's method. This is known as what? Merck's method. Okay. So what happens here is that we add sodium peroxide to an ice cold solution of 20% H2SO4. That means the reaction conditions are cool, right? As we have taken the ice cold solution of 20% H2SO4 and with constant stirring we add sodium peroxide, that will give you what? Hydrogen peroxide. Hydrogen peroxide, right? So upon cooling what happens, that Na2SO4 and H2O2 are obtained, right? So upon cooling what happens, that Na2SO4.10H2O, these crystals separate out from the solution, right? Now the solution will only contain 30% peroxide. Now the solution only contains 30% peroxide, right? However, from that 30% peroxide, you can obtain a pure sample of peroxide by vacuum distillation. By vacuum distillation. Again, I'll repeat the process. First, you add sodium peroxide to ice cold solution of 20% H2SO4, right? The resulting mixture or the resulting solution will have H2O2 and Na2SO4. Now you further cool it. What happens here, that Na2SO4 crystals separate out and the solution you are left with is peroxide. That is 30% peroxide. To purify it, that means to get the pure sample of peroxide, you may do vacuum distillation. This is known as what? Merck's method. Now, next is, let us say that we are having a dilute solution of hydrogen peroxide, right? And we want to make it concentrated. That means what? If you are diluting something, that means the amount of solvent that you are adding to a particular solute is large, right? While concentrated means that there is more amount of solute. Right, so if you compare the concentration of solute in dilute solution and in concentrated solution, the amount of solute in the solution is more in concentrated solution rather than that of dilute solution. Right, so what happens on dilution particularly, that concentration of solute is decreased, or you can say that we add solvent particularly to a given amount of solute, that is known as what? Dilution. So from the dilute solution of peroxide, we want to prepare concentrated one. So we need to follow the following steps. First one is the slow evaporation on water bath. So the dilute solution of hydrogen peroxide, first you take it in a evaporating dish, right? Now we particularly heat it in a water bath. What is a water bath particularly? You have here bowl like structure you have, and in that water is filled, and then you keep it on a burner, and on that particularly you will take peroxide in a beaker, let us say, or in a flask. You will take solution of peroxide and then heat it. You will not heat the peroxide on direct flame, right? We are taking a water bath here. So what happens here, that evaporation of water molecules takes place, right? While the solution becomes concentrated, it becomes 50% of H2O2. That means we have increased the concentration by removing the solvent. And how the solvent, that is water, is removed? By slow evaporation on water bath. You do not keep it on directly on flame. Is it clear? Okay. So evaporation in vacuum desiccator. So what is a desiccator? It is made up of glass actually, right? And a dehydrating agent is added there. What is a dehydrating agent? That means the agent which is used to remove water. Okay, whether it be silica, whether it be P2O5, or whether it be concentrated sulfuric acid, these substances act as a dehydrating agent. That means they remove water from the substance. So this 50% solution of peroxide is placed in a vacuum desiccator over concentrated sulfuric acid. So here this acts as a dehydrating agent. Now the rest of the water molecules are absorbed by these dehydrating agent, that is conc sulfuric acid, right? And now the 50% solution gets concentrated to 90% solution of peroxide, right? From 30% you are getting 50%, then from 50% you are getting 90%. From 30% to 50% you did slow evaporation on water bath. From 50% to 90% you placed it in a vacuum desiccator in which the conc sulfuric acid was acting as a dehydrating agent. Now from 90% you are obtaining 99% pure hydrogen peroxide by distillation. Distillation under reduced pressure, right? So what happens here is, because water is having a boiling point of what, 303 to 313 Kelvin, particularly water distills over this range, while you consider the boiling point of peroxide. Boiling point of peroxide was approximately, I guess, 423 Kelvin, right? And water is what? 373 Kelvin, right? So here what happens, that water gets evaporated first. Let us say what is a fractional distillation column. You're having a long column here, right, in which you are putting the solution. You are heating this on a burner, let us say, right, and a pipe is connected here like this. A condenser is placed here, and you are having a beaker here. Now this solution contains both water and peroxide both. Because water is having a low boiling point than that of H2O2, so it will evaporate first. Now when it will evaporate first, then it will condense because of the condenser, and the water droplets are collected here, right, while the H2O2 remains in the solution. So from 90% you can achieve 99% by distillation under reduced pressure. Now from 99% you want to obtain pure hydrogen peroxide. So how will you do it? That this 99% of solution of hydrogen peroxide is cooled in a freezing mixture of solid carbon dioxide and ether. Right. So what happens here is that crystals of peroxide separate out in the freezing mixture of solid carbon dioxide and ether. They are dried and they are remelted. This is how you obtain the completely pure hydrogen peroxide. I'll again repeat, from 30 to 50 water bath evaporation, then from 50 to 90 desiccator you are using, in which a dehydrating agent you have kept. Then from 90% to 99% you will do distillation under reduced pressure. Then from 99% to completely pure hydrogen peroxide, you will separate out the crystals of hydrogen peroxide using a freezing mixture of solid carbon dioxide and ether. Okay, so this is the process, that how can you obtain the concentrated solution of hydrogen peroxide from its dilute solution. Now see, peroxide acts as both. It acts as oxidizing agent also, and it acts as reducing agent also, right? So here you can see that it is acting as an oxidizing agent. Why? Because it is converting Fe2 plus to Fe3 plus, and it itself is getting reduced from H2O2 to H2O. Then here you can see that it oxidizes PbS2, particularly PbSO4, and then it reduces itself from H2O2 to H2O. Then in reduction you can see here that it it reduces manganese here from +7 to +2, while it reduces itself to water. Again here you can see that it is basically acting as a reducing agent, where HOCl is converted into Cl negative and H2O2 is converted into H3O plus oxygen gas. So this is very important. See, in particularly when it acts as an oxidizing agent, H2O2 converts itself to water. Okay, while in reduction what happens, that it converts itself to oxygen gas, that it liberates oxygen gas during reduction action in acidic medium. This way you can remember the reactions. However, these reactions will be more clear to you when we will study redox chapter. Then oxidizing action in basic medium. So see here that when it was doing oxidizing, or it was acting as an oxidizing agent in acidic medium, H2O2 was getting itself converted into water, right? While in basic medium, H2O2 converts itself to OH minus, and it oxidizes the other species, that is from Fe2 plus to Fe3 plus and Mn2 plus to Mn4 plus. Then reducing action in basic medium. So in basic medium it remains the same. Here also H2O2 was releasing oxygen gas. Here also it will form oxygen gas as a product, and it will reduce the other species. For example, iodine is being reduced into I minus, and MnO4 negative is being reduced into MnO2. So here the oxidation state of manganese is +7, while here the oxidation state is +4. How to calculate the oxidation state and how I am stating that why it is reducing, why it is oxidizing? If you have read the redox chapter, well and best. If you have not done the redox chapter, these all things will be clear to you in the redox chapter itself. Okay. Now the bleaching properties. So what is bleaching? Basically lightening the color, right? Lightening some substance is known as bleaching property. So it acts as a bleacher, or it has a bleaching action, right? So H2O2 on decomposition particularly will give you H2O plus nascent oxygen. This is known as atomic oxygen or nascent oxygen, which reacts with dye, and this dye gets oxidized and bleached. Okay, so this is the bleaching property of peroxide, that it is used to lighten the color, right? So dye plus the nascent oxygen which has been released by H2O2, or the atomic oxygen which has been released by H2O2, reacts with dye and bleaches the dye. Okay. Next is the acidic nature. So it is weakly acidic. However, if you take pure hydrogen peroxide, it turns blue litmus red. It turns blue litmus red. In daily life, it is used as a hair bleach. It is used as a mild disinfectant, right? Like in antiseptics also. It is used in manufacture of various chemicals, for example, sodium perborate or percarbonate, right? These two substances are used in high quality detergents. And it is also used in pharmaceuticals, particularly in the synthesis of hydroquinone, tartaric acid, or phalosporin, right? This is a pharmaceutical compound particularly which is used in medicines, right? So in synthesis of these three, peroxide is used. Next is the bleaching agent for paper pulp, leather, oil, fats, etc. Next, this is very important, that is, it is used in green chemistry. It is used in green chemistry, right? For example, in pollution control treatment of domestic and industrial effluents. So it is used in the treatment of pollution control, right? Basically the pollution which is released due to the domestic effluents or the industrial effluents, peroxide is used to treat that. Okay. Now next, storage. So this is an important thing that you need to remember about hydrogen peroxide, that on being subjected to light, peroxide decomposes into water and oxygen, right? So in the presence of light, this reaction is catalyzed. So therefore, the bottles of H2O2 are stored in dark, either in wax lined glass or either in plastic vessels. It is stored in dark because in the light acts as a the light particularly initiates the decomposition of peroxide. Or particularly, one thing you can do is that you can store it in dark. Second, you can add urea to that, so it acts as a stabilizer. Or you can add phosphoric acid, glycerol, acetanilide. So basically these are stabilizer which when added to peroxide, they prevent the decomposition of peroxide to some extent. And also that is very important that it is kept away from dust. Why it is kept away from dust? Because dust can induce explosive decomposition of the compound. That means if the dust is present and the decomposition of peroxide takes place, the reaction will be so exothermic in nature that it will release high amount of energy. Okay. These reactions are important. It liberates I2 from acidified Ki. That means if you take potassium iodide solution and add peroxide to it, it will give you iodine gas, which is having a purplish violet color. Okay, so this confirms the presence of I minus. Then lead sulfide, if you are having, it converts it into white. So PBS is basically black in color, lead sulfide. It converts PBS into what? White precipitate, that is PbSO4, right? So this confirms the presence of sulfide, S2 minus. Next, next is when 1 mole of PBS reacts completely with the H2O2, what happens? Hydrogen is liberated, oxygen is liberated, 4 moles of H2O2 is consumed, or sulfur is converted into sulfite. Tell me the answer. What should be the answer for the following question? You have to remember the reaction. PBS plus H2O2 will give you what? PbSO4 plus water. PBS plus H2O2 will give you PbSO4 plus water. Now balance this reaction. Balance the reaction and tell me what happens. Is the hydrogen liberated? No. Is the oxygen liberated? No. Is the sulfur converted into sulfite? No. It is converted into sulfate. So this is the reaction that 4 moles of H2O2 gets consumed. So when you will balance the following equation, you will get this. PBS plus 4H2O2 will give you PbSO4 plus 4 water. So that means 4 moles of H2O2 is consumed. So the answer is third. Now answer this question. H2O2 can be obtained when following reacts with H2SO4 except with. That means which one of the following will not react with will not react with H2SO4 to give H2O2. The question is that amongst these 4 compounds, which one will not react with H2SO4 to give H2O2? Anyone with the answer? Anyone with the answer for this question? See, if you will take this second, third and fourth, right? They all are peroxide because barium here is in +2 oxidation state. Sodium +1 but 2 will give you +2, right? Na2 +2. Then strontium is in +2 oxidation state. So it will become what? O2 2 minus. This will become O2 2 minus. This will become O2 2 minus, right? So this is a peroxide ion, that is O minus minus. But if you consider PbO2 here, lead is in +4 oxidation state. That means the O2 that is present here is not a peroxide linkage. That means, see, this is a peroxide linkage which is present as O2 2 minus. So here BaO2, Na2O2, strontium O2 all are having the peroxide linkage. Therefore, they react with H2SO4 to give you H2O2. But in case of PbO2, if you will take, the lead is in +4 oxidation state. So this become O2 4 minus, and it is not a peroxide linkage, right? Because the peroxide linkage is what? O2 2 minus. So as it is not containing any peroxide linkage, therefore it does not react with H2SO4 to give you H2O2. Okay, so the answer is first. Now this you should know. This you should answer. 2-ethyl anthraquinol, when oxidized in air, produces ozone, H2O2, H2O, or C2H5OH. This I expect you to answer correctly. What should be the answer for this question? 2-ethyl anthraquinol reacts with oxygen to give what? Ozone, H2O2, H2O, or C2H5OH, that is ethanol. Remember the industrial use we did? 3 benzenes connected. And then here OH, and then here OH. It reacts with oxygen in air to give what? Tell me the answer. Anyone? Remember the reaction was what? The alcohol was converted into ketone. One product was this. And one was H2O2. So this was the industrial preparation of H2O2. Okay, so the answer is, remember this reaction? This was the industrial application. Yes, Dinesh, you are correct with your answer. The answer is B. That is peroxide. Now this is a very important topic. Pay attention to this. That is strength of peroxide. Right? So this is the only numerical portion you can get from hydrogen and its compound. So we can express the strength of peroxide first as percentage, right? For example, I tell you that the strength of peroxide is 90% or 40% or 30%. What does that mean? That the percentage is by weight by volume percentage, right? So what is weight by volume? For example, I tell you 40% of H2O2. That means what? That 40 gram of H2O2 is present in 100 ml of solution. Similarly, I tell you 30% of H2O2, that means 30 gram of H2O2 is present in 100 ml solution. Again, I tell you 20% of H2O2, that means what? 20 gram of H2O2 is present in 100 ml solution. Right, so this is the strength of peroxide in terms of percentage. 40% will mean 40 gram of H2O2 in 100 ml. 30% will mean 30 gram of H2O2 is present in 100 ml. Then 20% of H2O2 will mean 20 gram of H2O2 will be present in 100 ml. Right, so this is how you can define strength of peroxide in terms of percentage. Okay. Now this is important as volume strength. For example, I give you that 10 volume of H2O2. 10 volume of H2O2. What does that mean? Right. So this line is very much important, that on decomposition of peroxide, what is the volume of oxygen that is obtained? That is known as volume strength. That means, for example, this reaction we have studied already, that peroxide decomposes to water and oxygen. It releases oxygen gas. So 1 liter of peroxide will produce how much oxygen gas at STP? That is known as volume strength of peroxide. For example, I give you that the strength of peroxide is 10 volume. Right? So what does 10 volume mean? That 1 liter of peroxide will give you 10 volumes or 10 liter of oxygen gas at STP. If I tell you, for example, that 20 volume of peroxide. So what does 20 volume mean? 20 volume will mean that 1 liter of peroxide will give you 20 liter of oxygen gas at STP. I hope this is clear. Right. So here just you have to remember that what is volume strength? The amount or the volume of oxygen which we are obtaining from 1 liter peroxide solution while it is undergoing decomposition at STP, that is known as what? Volume strength of peroxide. Right. So this volume strength particularly we need to convert, or basically we do a conversion with molarity and normality. We have to convert particularly that how with the help of molarity we can find out volume strength, and how with the help of normality we can find out volume strength. So this is the main aim. So first portion is that we need to find out the volume strength of peroxide using molarity. Right. Now what does molarity means? Molarity means what? Number of moles of solute divided by volume of solution in liter. This is molarity. Okay. So here we know that what is volume strength? Volume strength is that 1 liter of peroxide solution will give you how much liter of oxygen at STP. This is volume strength of H2O2. Now 1 liter we have to find out. See, 1 liter is what? Volume of solution. So I will put that 1 liter here. So molarity will be number of moles divided by 1. Right? That means number of moles will be equal to the molarity when the volume of solution is 1 liter. Because we have to find out the volume strength, and the volume strength is what? That 1 liter of H2O2 is giving how much oxygen. Right. So here the volume of solution is 1 liter. So molarity will be equal to what? Number of moles. This much you need to understand. Now next is, for example, let us say that 2 moles from the reaction we can infer that 2 moles of H2O2 gives 1 mole of oxygen. Right. That means what? That 2 moles will give you 22.4 liter of oxygen gas at STP, because we know that 1 mole of oxygen gas at STP is equals to 22.4 liter. This all you have learnt in your basic concepts of chemistry, right? So at STP it will be 22.4 liter. So this will mean that 2 moles will give you 22.4 liter at STP. Now because I am having m moles, remember that the number of moles equals to what? M, because the volume of solution was 1 liter. So m moles will give how much? M moles that are present in 1 liter of solution will give you 11.2 into m liter oxygen gas as STP. You just have to apply the unitary method, that if 2 moles are giving 22.4 liter of gas at STP, then m moles of hydrogen peroxide will give you how much amount of oxygen gas. So this will be what? 22.4 divided by 2 into m liter of oxygen gas at STP. So this becomes what? 11.2 into molarity. So this much amount of oxygen gas will be obtained at STP. For numerical purpose, you can just remember that volume strength of peroxide, volume strength of H2O2 equals to 11.2 into m at STP. Okay, because volume strength was what? That how much amount of oxygen gas will be evolved when 1 liter of peroxide solution will be decomposed. So if 1 liter of peroxide solution is having m moles, then if 2 moles are giving 22.4 liter at STP, then m moles will give 11.2 into m liter at STP. So this will be the volume strength. Okay. This formula, final formula, you can remember that volume strength equals to 11.2 into molarity. Okay, this formula you have to remember finally. Now next is using normality. See, using normality we know that what? That molarity into n factor or the z factor you may call it is equal to what? Normality, right? This we can use. See, volume strength equals to what? 11.2 into molarity. Okay, so volume strength can also be written as what? 11.2 into what is molarity? Normality divided by n factor. So this will be normality divided by n factor. Now the purpose is to find out what? The n factor of peroxide. So we know that for ionic compounds, how do we find out the n factor? So it will be what? H2O2 is made up of 2 types of ions, one cation and one anion. So it will be 2H plus and O2 2 minus, if you consider it as it is an ionic salt, right? So here the n factor will be what? 2. N factor of peroxide will be 2. So this will be 11.2 into normality divided by 2. That will give you what? 5.6 into normality. So volume strength can also be written as 5.6 into normality or 11.2 into molarity. Okay. Again we'll have this. I'll revise the concept that H2O2, the total cationic charge is 2. So particularly the n factor will come out to be 2. Normality equals to molarity into n factor, that is 2. Normality by 2 will be equal to molarity. When you substitute this in the first formula, you will get the final formula as volume strength equals to 5.6 into normality. So final 2 formulas you have to learn. One is volume strength equals to 11.2 into molarity, and the second one is volume strength equals to 5.6 into normality. These 2 formulas you have to learn. Okay. Now next is volume strength of peroxide using percentage strength. If you know percentage strength, remember that what was percentage strength basically, that if it is mentioned as 40%, that means what? That 40 gram of peroxide is present in 100 ml solution, right? So that was what? Weight by volume percentage. So here let us say that P is the percentage of H2O2 solution, right? For example, I write it as 40%, 30%, 20%, I am writing it as P%. So if P is the percentage of peroxide solution, that means what? See, if 40% was there, that means that 40 gram was present in 100 ml. P percentage will mean what? That P grams of H2O2 is present in 100 ml. But volume strength, we have to consider that 1 liter of H2O2 solution is there. So we want to find out that how much peroxide is present in 1 liter. So if in 100 ml, P grams is present, so in 1 liter, that equals to 1000 ml, 10 grams of P will be present. Right, I'll again repeat, if in 100 ml, P grams of H2O2 is present, then in 1000 ml or in 1 liter, 10 P gram of H2O2 will be present. Okay, now I want to find out the number of moles of peroxide, right? We know that the given mass of peroxide is what? 10 P gram, right? And from the formula, that number of moles equals to what? Given mass, that is 10 P gram divided by molar mass. So if you calculate the molar mass of H2O2, that is 2 plus 16 into 2, that is equals to 32. So 32 plus 2 will give you what? 34. So molar mass, given mass divided by molar mass. This will give you what? Number of moles. So the number of moles come out to be what? 10 P by 34. So finally we have obtained that the number of moles is 10 P by 34. Okay. Now we know that if 2 moles of peroxide gives 1 mole of oxygen at STP, or you can say that 2 moles of peroxide will give you 22.4 liter of oxygen at STP, then this amount of moles of H2O2 will give you how much amount of oxygen gas? That will be the volume strength. So again the unitary method, if 2 moles is giving 22.4 liter of oxygen, so these many moles will give what? 22.4 divided by 2 into 10 P divided by 34. This is the amount of oxygen that will be given by 1 liter of peroxide. That means this particular thing will be your volume strength. Okay, so I'll simplify this formula. On simplifying this formula, basically you will get what? That volume strength equals to P into 56 by 17 liter at STP, or you can remember that P into 56 by 17. What is P? P is the percentage strength, 40%, 30% depending upon the numerical you are solving, right? So P is the percentage strength. Volume strength equals to percentage strength into 56 divided by 17 at STP. Okay. I hope this much is clear. So 3 formulas you need to remember. One is this formula, that volume strength equals to percentage strength into 56 by 17. Then you can remember that volume strength equals to 11.2 into molarity. Then you can remember that volume strength equals to 5.6 into normality. Okay. Yes, it was 5.6. Yeah. Now you solve this particular question and let me know the answer. Solve this particular question and let me know the answer. The question is saying a certain sample of hydrogen peroxide is 1.5 molar solution. That means molarity is given as what? 1.5. Right? You have to find out the volume strength. You have to find out the volume strength. Direct formula you have to apply. Calculate and let me know the answer. Anyone? Volume strength equals to what? Formula just you have to use. What was the relation? Volume strength equals to 11.2 into molarity. So molarity is given. Can you find out volume strength? Yes, Sarayu, you are correct with your answer. The answer is 16.8. So it will be what? 11.2 into what is molarity? 1.5. That will give you 16.80. So this is the volume strength. Good. Next question is, calculate the strength of 10 volume solution of hydrogen peroxide. Calculate the strength. Strength means percentage strength you have to find out. Percentage strength. Remember the formula? What was the relation between P and volume strength? 56 by 17 into P. Volume strength equals to 56 by 17 into P. Apply that formula and let me know what is P. Apply the formula and let me know the answer. Okay, Dinesh is saying 3.03. Yes, you are correct with your answer that the answer is 3%. Good, because volume strength is given as 10. So this will be 56 by 17. Percentage strength you have to find out. So this will be what? 170 divided by 56 equals to P. That will approximately come out to be equal to 3%. Dinesh, you are very much correct with your answer. Good. Now we will study about, we are just having an idea about hydrogen economy, right? So this is the last topic of the chapter. See, basically what is hydrogen economy? By comparing the amount of energy that is released by using hydrogen as a fuel, or LPG as a fuel, or methane as a fuel, or octane as a fuel in the liquid state, these are the values that we are obtaining, right? For example, 1 mole of dihydrogen will give you 286 kilojoule of energy. 1 mole of dihydrogen as a liquid will give you 285 kilojoules of energy. 1 mole of LPG will give you this much amount of kilojoules of energy. 1 mole of methane will give you 880 kilojoule of energy, right? And so on. Similarly, here also 1 gram of dihydrogen will give you 143 kilojoule of energy. 1 gram of dihydrogen as a liquid will give you 142 kilojoules of energy. So this is the gist of the table, right? So we have found out that dihydrogen can release more energy than petrol. More energy than petrol. Here you can see that octane in the form of liquid, it is giving from 1 gram we are obtaining 47 kilojoules of energy. But here if you see in dihydrogen, you are obtaining what? From 1 gram of dihydrogen, you are obtaining 143 kilojoules of energy. That means you can obtain more energy from hydrogen than that of petrol using the same amount of hydrogen and petrol. And moreover, the second thing is that pollutants in combustion of dihydrogen are lesser than that of petrol, right? So basically our science is trying to, find out a way in which we can use dihydrogen as a fuel instead of petrol. So the only pollutants that are present in the dihydrogen is the dinitrogen, right? So basically if you inject a small amount of water in the cylinder which is containing dihydrogen and dinitrogen, that will lower the temperature. So on lowering the temperature, what happens? That the reaction between dinitrogen and dioxygen do not take place, right? So you can remove that impurity of dinitrogen easily. Now, what are then the limitations that we are still sticking on to the petrol, right? We have not, switched on to dihydrogen as a fuel. So, First point is that the mass of the containers in which dihydrogen should be kept is very much high, right? For example, you can see here that a cylinder of compressed dihydrogen weighs about 30 times as much as a tank of petrol containing the same amount of energy. That means for petrol you need to have a small tank, but for hydrogen you need dihydrogen to particularly use it as a fuel, you need to have a 30 times heavier tank. Okay, so this is the first limitation. Second is that dihydrogen converts basically into liquid state when it is cooled to 20 Kelvin. Right, so at 20 Kelvin temperature, what happens? That dihydrogen gas converts it into a liquid state. This is the second disadvantage of using hydrogen as a fuel. Okay, so basically to store dihydrogen, we use metal alloy tanks, for example, sodium, nickel, titanium hydrogen, magnesium hydrogen. These kinds of alloys we use to store dihydrogen in small quantities. Now, principle of hydrogen economy. So, basic principle is that how do we transport and store energy in the form of liquid or gaseous dihydrogen? That is the basic principle of hydrogen economy. Okay, so advantage of hydrogen economy is that basically we want to use the energy that is transmitted in the form of dihydrogen and not as electric power. So, overall in this topic you need to learn that what are the advantages of using hydrogen as a fuel and what are the disadvantages of using hydrogen as a fuel, and what do you mean by basically hydrogen economy. The hydrogen economy is basically that how do we transport or store energy in the form of liquid or gaseous dihydrogen. So first attempt in India for hydrogen economy was that a pilot launched a pilot project was there, right? He used dihydrogen as a fuel in October 2005. So basically he initially mixed 5% dihydrogen with CNG to use for four-wheeler vehicles. Okay, so the first attempt was what? That in October 2005 dihydrogen was used as a fuel for a pilot project. Second was that 5% dihydrogen was mixed with CNG for the use of four-wheeler vehicles. Third was that the percentage of dihydrogen could be gradually increased to reach the optimum level. Particularly basically to minimize the use of CNG, we can increase the amount of dihydrogen. Okay. Now this is the last topic, that is the hydrogen fuel cell for generation of electric power. So basically to generate electricity we use hydrogen fuel cell. You just need to have an idea what is a hydrogen fuel cell, right? So there are carbon electrodes. The electrodes are made up of carbon, right? And aqueous sodium hydroxide solution is used as the electrolyte. Catalysts are also there. What are the catalysts? Platinum and palladium, which are finely divided so that their surface area can be increased. Okay, they basically increase the rate of electrode reactions. So on cathode what happens? That oxygen gas converts into OH minus. At anode what happens? That hydrogen gas converts into water. So the overall reaction becomes that hydrogen plus oxygen will give you water. Here you can see that this is the hydrogen inlet. These are the anode and the cathode. So here at anode what happens? That this hydrogen is converted into water, and at cathode what happens? That O2 here is converted into OH minus. So overall, and here you are keeping what? Aqueous electrolyte. So overall water is generated here. Okay. So that was all about hydrogen chapter. Structures you need to remember, and heavy water is important from its application point of view, that it is used as a moderator in the nuclear reactions. Then hydrogen economy question can be asked like, what is the basic principle of hydrogen economy? What are the disadvantages of using hydrogen as a fuel? When was the first attempt made to use hydrogen as a fuel? These questions can be asked. Structure of H2O2 is very much important. Preparation of H2O2 is important. Okay. and resemblance of hydrogen with that of alkali metals and halogens is also important, and how particularly hydrogen differentiates from the halogens, that is also important. Okay, so overall the sessions, if you particularly revise, and NCRT you can follow, that is sufficient from the examination point of view, right? So the NCRTs you can follow, and the sessions you can revise. I think that will be more than sufficient for any competitive examination. And also the numericals on volume strength are very much important. Just you need to remember the 3 formulas. You don't need to remember the full derivation, however I have explained that. So you can remember the direct formulas and use it in the numericals. Okay, so that's all for today. Happy learning to all.